We are now starting module 6, which will be about extraction of metals from sulphides, and we will start with copper metallurgy. Now, I have already said one or two things as an introduction during my last lecture, but let me repeat what I said. In this module 6, our learning objectives will be the following: complex nature of sulphides and sulphide metallurgy. Then we will take pyrometallurgical extraction processes for copper, zinc and lead. These are three very common metals, often called base metals. We will perhaps touch nickel also, because nickel is also found as sulphides, also found as oxides. Then hydrometallurgical extraction processes for copper and zinc, not really for lead. Then we will talk about the concept of process fuel equivalent. That gives us a way of comparing energy requirements. Now, these are the standard methods of producing metal from sulphides. One is straightforward thermal decomposition. This is applicable in the case of mercury sulphide HGS, which can be simply heated and it decomposes to give mercury metal and sulphur. Most common and logical will be to take the sulphide, roast it to make an oxide and then reduce by carbon like you treat an oxide. The third one is what will apply in the case of copper and also in the case of nickel. We will see when nickel is in the form of sulphide. In this case, the idea is not to roast copper sulphide to copper oxide and then reduce by carbon. It is a very different technique. Copper sulphides are often associated with iron sulphide, and if we try to roast them, iron gets oxidized in preference to copper. So, initially iron will start forming iron oxides. We ensure that not all iron gets oxidized. We leave oxidation of iron incomplete. The iron oxide that forms FeO is slagged out. We are left with copper sulphide and some residual iron sulphide. These two form what is known as a matte. Matte is a mixture of sulphides. From there we get metal by a very interesting oxidation technique, where simply by oxidizing it we produce copper. How we will do that we will see later. The other will be flash smelting, where roasting, smelting are combined, they speeded up, the process is speeded up. We can also have metallothermic reduction of sulphide. There can be hydrometallurgical processing of sulphide. A sulphide can be chlorinated, changed into a chloride, from which the metal can be extracted by electrolysis or by a metallothermic reduction. Finally, there is also a process, in some cases matte, which is a mixture of sulphides, can be refined to produce pure metal by an electrolytic process. The commercial process is for nickel only. Let us start with copper. Now, I mentioned that there is a beneficiation technique called flotation, which makes it possible to concentrate low grade copper ores to produce a concentrate that will have much higher concentrations of copper. And flotation, as I mentioned, is a technique where we have very fine ores, ores is ground very fine, then we make a froth, we have that fine suspended in a medium where there is a froth, and when the bubbles come out, the sulphide particles attach themselves to the bubbles, they float to the surface. The gangue minerals, silica, other oxides which do not attach themselves to the bubbles, they stay behind. So, from the top we can skim out a layer which will be very rich in the sulphide particles. So, starting with an ore which may contain only 1 to 2% copper, one can, after grinding and flotation, one can produce a concentrate which will have 13 to 35% copper depending on circumstances. And the gangue and the other sulphides which have not been floated will be taken out. There is a way of doing differential flotation also, that you float one sulphide, not the other sulphide, then another step float the other sulphide. So, here we are doing a differential flotation only to get the copper sulphide mineral floating out, other gangue and other sulphides, and there are other sulphides are not floated. So, the conditions are so maintained. So, we will start now with a concentrate which contains as sulphide 15 to 35% copper. This is the starting material. Now, there are several ways which are similar, but they have evolved over time. The conventional or traditional route is this: the concentrate goes for reverberatory or electric furnace smelting, or it can go from hearth or fluid bed roasting, calcination, and then go for a reverberatory or electric furnace smelting. Now, in this smelting process, I have mentioned little while ago, the aim is not to produce an oxide, but to have controlled oxidation so that we produce a matte. Matte is a mixture of copper sulphide and iron sulphide, which means that copper sulphide which was in the concentrates is left practically untouched. Only the iron sulphide part is oxidized, that too incompletely, so that only it goes to the FeO stage, that FeO is slagged out, and the rest of the iron sulphide and copper sulphide, they form a sulphide solution called matte, which can have 35 to 60% copper, the rest will be iron as iron sulphide. So, all the oxygen has been eliminated from the system, and the slag that comes out, which has most of the iron slagged out, FeO with silica, limestone, quartz, etc. in a slag, it will also take out a small amount of copper, obviously that we cannot ensure. But basically oxygen is eliminated from the system, but what we get is a matte mixture of iron sulphide and copper sulphide. Then this goes through a process called converting. Converting, a process of oxidation where as we oxidize iron sulphide and copper sulphide matte, a stage comes where suddenly copper comes out of the system. And there is some slag also. The slag will be put back to the reverberatory furnace because it may contain some iron. The copper that has come out goes for refining. Now, an newer route is that which will eliminate reverberatory furnace smelting, we would have, and these steps everything is combined into one step called flash smelting. Means everything is smelted, calcined and flashed very fast, produce a matte, it goes straight for converting. There are even newer processes where everything is combined, all steps are combined into one continuous smelting process, which can produce either matte for conversion or it can straight away produce the copper called blister copper. What it is, I will tell you later. And the slag that contains some copper will go for slag cleaning for copper recovery. After we have produced impure copper called blister copper, which is 98.5% copper, it will go for refining. In the refining process, we will produce cathode copper 99.99% copper, but we will also get whole lot of valuable byproducts in a slime, all the precious metals, silver, gold, platinum, palladium, etc., etc. I will go into the details of the process now and look at these steps one by one. Now, to understand what happens when we roast this sulphide concentrate in a reverberatory furnace, we should note that during roasting, sulphides are first oxidized, iron sulphides are first oxidized in preference to copper sulphides. Now, we do not want iron sulphides to form Fe2O3, because if Fe2O3 forms, then this cannot be slagged very easily. It does not dissolve in the slag that you are creating by adding limestone, quartz, etc. And the gangue, there is a slag phase, Fe2O3 does not dissolve very well, but FeO does. So, the iron sulphides will be oxidized only up to the FeO stage, not beyond. Sometimes they say little bit of Fe3O4 is okay, because that helps in protecting the refractory, it goes and gets absorbed on the refractory surface. But let us ignore that. We have iron sulphide and copper sulphide in the starting material. We will ensure that one does not go beyond FeO, which means we will have to leave much of FeS not oxidized, that is acceptable. So, the FeO that forms will go into the slag phase. No copper oxide is formed, because we have not even completed oxidation of iron sulphide. Copper sulphide cannot be oxidized unless you have oxidized the whole of iron sulphide. We are not oxidizing whole of iron sulphide. Only part of that is oxidized, only up to FeO stage, that is taken out. Iron sulphide and copper sulphide left behind will form matte. No copper oxide is formed, so the slag will not have copper oxide. We have mentioned only very minor amounts of copper oxide will go into the slag. And we are deliberately leaving FeS behind to ensure that Fe3O4 and Fe2O3 are not formed. This is the basic technique. Now, during smelting, like this, subsequently, if there is some Fe2O3 left, if supposing by somehow Fe2O3 forms, then in the subsequent step, the residual FeS that we have will reduce Fe2O3 and Fe3O4 to lower FeO state, and that will be slagged off. So, we want that FeS to play this role also. We must have some FeS that subsequently, if there are higher oxides, they will be reduced to the FeO stage for slagging. This stage smelting is coming after now. So, our aim is to produce only a mixture of copper and iron sulphides. FeO is removed in slag, Then we will go for what is known as converting. Converting is where we start oxidizing the matte. Now, first that iron sulphide is oxidized to produce FeO, that is removed in a converter, and then copper sulphide starts getting oxidized. Once it reaches the Cu2O, when it forms Cu2O, then there is a very interesting reaction between Cu2s and Cu2O that forms copper straight away. The reaction is written as Cu2s plus 2 Cu2O to produce copper and SO2. So, what is it we are doing? Starting with a sulphide concentrate, we have roasted it to ensure that we are left with incomplete roasting of iron sulphide. We will produce a matte, and then we will have a smelting process. In the smelting process, residual FeS will ensure that Fe2O3, Fe3O4 form FeO, that is slagged off. Then we are left up with the matte which will go for the converting step, where in a converter oxygen will be blown to oxidize iron sulphide to FeO stage, and it is slagged off. And once copper starts getting oxidized, once it forms Cu2O, these two will react and it will produce copper straight away. Now, all the reactions that are taking place are exothermic. So, in theory, you are not supplying any energy, but in practice that is not so, because when you have a reverberatory furnace or an electric furnace where you do the smelting operation, obviously there will be a lot of energy losses. So, energy will have to supply, but the converting step where you have a molten matte and oxygen is being injected, it is a highly exothermic process, no external heat supply is required. So, what are the reactions? We first have a roasting reaction. See, the copper sulphide is mineral is CuFeSt S2. It tends to form CuO and Fe2O3. It tends to form sulfates. It can decompose to give Cu2s and Fes also. It can give Fe2O3. It can give CuO, CuSO4, FeSO4, this compound. Like the roasting of sulphides, all kinds of phases can come about, but our aim will be to control the partial pressure of oxygen, partial pressure of SO2 in such a manner that we will essentially have Cu2s, Fes and FeO, and that FeO during the smelting reactions which will take place at 1250s with fluxes, it will produce two layers, a slag layer which will remove the iron part, and we will have a matte metallic sulphides, a mixture of iron sulphide and copper sulphide. Then during smelting, in a smelter we will continue with oxidation. Many reactions can take place. If any CuO is there, it will convert itself to Cu2s, forms FeO, it will be slagged off. If sulphate is there, it will form Cu2s, it will be slagged off. Everything is molten and many reactions take place. And then finally, by smelting we will have iron sulphide and copper sulphide. Now, we have to remove iron and sulphur and other impurities from the matte, and we will do that by slagging. We will continue in the converter, we blow oxygen. to oxidize FeS to FeO stage. Then FeO will react with SiO2 to form ferrite slag. It will go into the slag phase. The slag will contain 1 to 5% calcium oxide, magnesium oxide. Iron will be mostly 40 to 50%. There will be some slag losses may be there. It would have silica. So, in the converter where the molten matte is being oxidized by blowing oxygen, these reactions take place. How do we blow oxygen? We will see that at one time attempts were made to blow oxygen from the bottom, like it was done in the Bessemer converter, air was blown. But in copper converter things, oxygen comes from the side. Why it is from the side, I will discuss little later. And once we start doing that, we automatically will produce blister copper. Blister copper means, because once that copper is formed and is solidified, and if it is broken, it has a structure like blisters. There are lots of holes. So, that is why it is called blister copper. And the reactions are that in the matte there is copper sulphide. It reacts with the oxygen coming in, produces Cu2O. Gradually Cu2O start converting into Cu2 at one stage. Once you have twice as much Cu2O as Cu2s, then these two react very quickly with each other to produce copper liquid and SO2 gas. The overall reaction is Cu2s being oxidized by oxygen to produce copper and SO2. So, the entire process, a lot of SO2 will be coming out. The whole thing is exothermic, all the reactions. The only energy required is to make sure compensate for the heat losses that go from the high temperature reactors. You do not need any heat supply during the converting reactions, because they are very highly exothermic, like the today's steel converters, where pig iron, the oxygen is injected into pig iron to produce steel. You do not need any external heat supply. The same thing is also in the copper converter. But in the smelting stage, which is done in a reverberatory furnace or an electric arc furnace, also although you have exothermic reactions, you will need heat supply. Now, these are the two kinds of reverberatory furnaces used for smelting. This is the conventional reverberatory furnace, which uses liquid fuel or gaseous fuel. You have air and oxygen coming in, there is fuel coming from this side, the converter slag will be taken out this way, matte will come out this way, outgoing gases will go out this way. Now, there are many complications of this design, I need not go into that, but you see the flame is thrown from this side, and this is the feeding drag converter, and things are happening inside a long converter. There are also submerged arc electric furnaces, where energy is not supplied by oxidation of a fuel, but by electrodes that stick into the molten charge. So, this is a cutaway view of submerged electric arc furnace, and this is a cutaway view of a reverberatory furnace. Now, let me read out what is written here. Conventionally, a smelting operation is carried out in a reverberatory furnace filled with either coal, fired with either coal or oil. A typical reverberatory furnace is shown. Smelting has also been carried out in electric furnaces, that is also shown. An electric furnace is more advantageous than a reverberatory furnace if the hydroelectric power is available freely. If you have the hydroelectric power supplying, then you will go for an submerged hydroelectric furnace. And it is also done inexpensively, because the generation of large volume of combustion gases is avoided. When you are using coal or liquid fuel, then as it is lot of SO2 is coming out from the system, but you would also generate CO2. The amount of gases, combustion gases coming out will be much larger. In the arc furnace, you are only getting SO2, you are not getting CO2 that will come from combustion of oil or coal. So, that will be an advantage of electric arc furnace. However, the electric arc furnace can only be operated where electricity is available. Unfortunately, an electric arc furnace consumes a large amount of energy. When fossil fuel is burnt, especially to generate electricity, because it is a roundabout way of getting energy. If you are using a fossil fuel into the furnace, either furnace oil or coal, and you are generating heat directly, the process of heat generation will be much better. But when if you are getting electricity that has been generated in a thermal power plant, again by combustion of fossil fuels, then you have a two-step thing, that you are generating at some point, from there it is giving electricity, which electricity is being consumed here. So, if this electricity for the submerged arc is coming from a thermal power plant, then you are not generating CO2 here, but you are generating CO2 elsewhere where the thermal power plant is located. If it is hydroelectricity, this problem is not there. Otherwise, you have to remember that you have only displaced the problem of combustion gases in this case, if thermal power plant is giving you the electricity. But then in this process, in the plant, you are generating less amount of combustion gases, because you are only generating what is coming from the reactions, which does not include a combustion reaction. Now, there are both of these have now given away to flash smelting and continuous smelting operations, which I will discuss little later. Now, in the early days of copper concentrate smelting, the average capacity of the reverberatory furnace was only 100 tons per day, but at present it has gone to almost 10 times that much, 1000 tons per day. Now, when a reactor becomes bigger, then relatively energy losses would be lower. So, it will be more energy efficient. When reactors are smaller, imagine 10 small reactors with 10 times as much as surface area as compared to something with capacity 10 times larger. This will have lesser surface area, surface to volume ratio, therefore, heat losses will be less. So, the tendency is to make the reverberatory furnace as big as possible. But then trying to operate with a bigger furnace also has operational problems. There will be other kinds of problems. So, the industry has to decide what it can do. So, this is the step where you produce from the roasted material a matte. A matte, as I said, is a mixture sulphide. This matte will go for converting. The purpose of converting is to remove iron. Part of that iron you have removed earlier by making FeO and removing partly, but again lot of that iron that is left there as FeS will be removed in the converting step. Sulfur and other impurities from matte will also be removed. For this, the molten matte is produced as a result of smelting. The molten matte produced from the smelting step is charged into a side blown converter, which is a cylindrical vessel. I will show you a picture of that, with a capacity of 100 to 20 tons per of matte. It is not a continuous process, because you charge the matte, it is like steel making. You will produce blister copper, pour it out, then take fresh amount of matte and again do converting. So, at a time you will produce 100 to 20 tons of matte. A typical vessel will be 4 meters in diameter, 9 meters in length. So, it is a big cylinder and is lined with a layer of chrome magnesite refractory about 40 centimeter thick. Now, next figure shows you a typical side blown converter. This is the cylindrical vessel. There are pneumatic punchers, so that it can be rotated if necessary. This is the hood from which this is necessary because you will have to pour out blister copper. So, that thing has to rotate. 2 air pipes through which the oxygen will be blown in. There is intake of siliceous flux because you have to create a slag. There is a flux gun, how the gun it will be thrown into that, etcetera, etcetera, etcetera. Gases will come out of here. All the details are there. This is more important. See, this is the converter. I am looking at it from the sectional point of view. It is charged. This is the hood. At every step, whatever gases are coming will go out to this hood. Then this is straightened up, put straight under the hood. We start blowing oxygen from this side, and after it is blown, we can tilt it the other way, pour out the product which is blister copper. So, charge, blow, tilt the other way, fully take out the blister copper. This is the converter operation. Now, in the converter, the atmosphere is highly oxidizing compared with the neutral or mildly oxidizing atmosphere during smelting. Air or oxygen enriched air up to a maximum limit of 32 volume percent of oxygen in the blast is injected into the molten matte through 2 ears. Each 2 ear is about 5 centimeter in diameter, and there are about 40 2 ears in a converter. The total volume of gas flowing through these 2 ears is about 600 meter cube per minute. The products of the converter are slag and blister copper. So, you have 3 steps. You have roasting, then converting, smelting, and then converting. Now, let us come to what is happening during converting. So, during converting, you have starting with a mixture of sulphides, copper sulphide, iron sulphide. Then iron sulphide is converted to FeO, it is taken out as a slag. You are left now with a metal, very often it is called a white metal because it looks white, it is copper sulphide. Now, it is copper sulphide's turn to start getting oxidized. You gradually begin to build up Cu2O, and then you create 2 layers. What are these layers? That will come if you look at the phase diagram here. Let me go through this first. The relative volumes of the 2 layers can be determined by the lever rule. When the sulfur level eventually drops to 1.2%, only the metallic copper phase remains. At this stage, care to be exercised to ensure the metal is not over oxidized Cu2. Now, as I said, there is a stage comes when Cu2s reacts with 2Cu2O to produce copper, and you are left with copper and copper sulphide. And in that case, you will get 2 layers. Air is coming through this layer, and this is the phase diagram of copper and copper sulphide. You see, there is a complete separation here. This is the melting point of copper, melting point of copper. This is the melting point of copper sulphide. Now, if the converting operation is taking place here, you are going from copper sulphide towards this direction, you go from A to B to C to D, and there is a clear separation between here and here. There is a copper layer with very small amounts of sulfur, and you have copper sulphide here. This is the two layers you are getting, and you are injecting air continuously into the copper sulphide layer. Copper is at the bottom. The completion of blow can be determined by casting a small sample of the copper taken from here and is examining the fracture of the sample. The blistery appearance of this sample lends to the name blister copper to this product. In industrial practice, the blister produced contains 0.02 to 0.05% sulfur along with 0.2 to 0.5% dissolved oxygen. So, the blister copper we are producing here, you will find there is always a bit of sulfur, and it will also contain some oxygen, because after all you are injecting oxygen. Now, attempts made in the early days to produce blister copper in the bottom blown converter used in the steel industry ended in a failure. Now, of course, there is top blown converters, but Bessemer converters had oxygen coming from the bottom. So, same thing was tried in the case of copper. It ended up in a failure because after point B is reached, once you have reached this point B, you are coming from copper sulphide part to the copper part. Once you reach this point, means after you have removed certain amount of copper sulphide and produced certain amount of copper, the relative amounts you will know from the lever rule. A layer of copper rich liquid will be formed at the bottom. So, once you start producing copper, you have gone this way, a copper rich liquid will be formed at the bottom in contact with the tuers, and there will be very little heat generation due to Cu2s oxidation in this layer. There is no more Cu2s left. Cu2s oxidation is generating heat. Once it produced copper, the copper would sink and cover the tuer, and because there is no heat being generated, you have a problem there. There will be very little heat generation due to Cu2s oxidation, though this heat is generated, though heat is generated due to oxidation of copper, but there is not much difference in the heat generated per mole of oxygen for copper oxidation and that for Cu2s oxidation. The efficiency of copper oxidation is much lower. Consequently, the temperature drops rapidly in the tuer zone of the Bessemer converter. This leads to the clogging of the tuers with solid and stoppage of the conversion of the matte to the metal. So, if we are trying to inject from the bottom, after some time the process will have to be discontinued, because as copper sulphide begins to produce copper metal, that metal will come down to the bottom and then it will get frozen, and then it will stop the, it will interfere with the incoming oxygen. So, the tuers will be clogged with the solid and the conversion of the metal matte to metal will stop. So, then the industry had to come up with the invention that have a side blown converter, and the conversion of white metal to blister copper in a converter becomes possible. So, from the side oxygen will be blown into the Cu2s layer, copper goes on forming, it goes to the bottom almost pure copper, and copper. So, this layer gradually becomes thinner and thinner, and this layer becomes thicker and thicker. When it is all over, this entire converter will be turned and the blister copper will be taken out. This is how the converter operates. Now, again I am repeating what I have said earlier, that the oxidation taking place during roasting and that resulting from the leakage of air into the furnace during smelting determines the extent of oxidation of the iron sulphide in the charge to the slag. During roasting, it is an oxidation process. There is some leakage of air also into the furnace during smelting. All these tends to oxidize iron sulphide to iron oxide, and it goes into the slag. Generally, the object is to produce a matte, there should be an E, that contains 35 to 45% copper, 20 to 25% sulfur and 25 to 30% iron. In the matte, this iron is as sulphide, that copper also is a sulphide. This not only minimizes the loss of copper to the slag, but also provides a matte, again there should be an E, with a sufficient quantity of iron sulphide for use in the next stage. Now, in the next stage where there is converting, the iron sulphide oxidation will provide all the heat required to ensure an autogeneous converting operation. You need to have certain amount of iron sulphide, because that will oxidize and begin to give you lot of heat. So, that you do not need any extra heat in the converter. Now, the relationship between the percentage copper in the slag and that in the matte is given in the figure. Lot of experiments have been done in the industry to find out how to cut down copper losses in the slag. What has been found is something you should expect from common sense, that if you have a very rich matte with a lot more copper, then copper losses in the slag perhaps will also be more. That is what it says. The relationship between the percentage copper in the slag and that in the matte is shown in the figure for various reverberatory furnace operations around the world. So, wherever we are producing matte in the smelting step, data have been taken and have been found that percentage copper in the reverberatory furnace matte, the higher it is, the higher will be the copper losses in the slag. But it is never more than 1%. The copper losses are not that alarming. Okay. Now, once we have produced a blister copper, we have produced an impure copper. That copper will now have to be refined, and refining of copper is a very elaborate process, in the sense that it will give whole lot of products. Let us see how. One is, first of all, there is some sulphur. The sulphur can be removed from the liquid copper by slow oxidation. If we have the copper pool, the blister copper in the molten state, and is slowly oxidized, then all the sulphur will be removed as SO2. Some copper might get oxidized also, and in the process some oxygen may go into the copper. So, to eliminate that oxygen now, the industry years ago have found a very simple process which is still applied in the industry. There is a pool of copper which has to be refined, it has impurities, it has sulphur. That sulphur is removed by keeping it through a slow oxidation, that can be done in a reverberatory furnace. Just keep the door open and the air leakage itself to gradually remove all the sulphur. But the air also then goes into copper, we want to remove that. That is done by a process called polling. Polling is stirring the path with green branches taken from trees. It is a very crude process, but very effective process, and industry even today applies that technique. When green branches are taken from trees and those branches are used to stir the bath, those branches generate reducing gases like methane, and the methane will reduce the oxygen. People have tried in modern industry to remove that oxygen by hydrogen injection, but that is too elaborate and too complicated. Industry still uses poling. It is stirring by green branch trees. This is done in 400 ton capacity reverberatory furnace over 12 to 16 hours, door kept open to mild air blast. This is the technique. Now, during the slow oxidation, many other things are also removed: sulfur, iron, selenium, zinc, solid oxides being skimmed off, and poling is done at the end. So, initially we allow a lot of oxidation of the bath for many hours, and oxides keep on floating to the surface and they are skimmed off. We allow all the impurities mentioned to get oxidized and get removed. When we are sure that all those have been gone, we know there is a lot of oxygen has gone in now. So, it will be poled using green branches. So, poling is done at the end. Though the method is crude, it is still the most common method. Now, finally, after you have removed all these impurities by slow oxidation, we get a copper which is 99.7% pure. Now, this copper has to be refined further, and it will be done by electrolytic refining, which is done in concrete or wooden tanks. Dimensions are roughly given, using 250 to 320 kg copper anode, a thick anode which is that impure copper, in a copper sulphate solution, 35 gram per liter in sulphuric acid. This is not 9, it should 0, with some additives like glue and alcohol. Why glue and alcohol? Because we get a nice cathode deposit. Now, the scheme is simple. The impure copper will be made into a thick anode, and there is a pure copper sheet cathode. We have the electrolyte with copper ions in that. As electrorefining starts, copper will dissolve from anode and it will get deposited on the cathode, using glue and other additives to make sure that the deposit is very coherent. So, this gradually becomes thinner, this gradually becomes thicker. Now, what happens when copper is coming from here to here? What happens to the impurities that are within this? Now, there are two things can happen. There are some metals here which enter the solution because they can dissolve in the solution. Like if you have impurities like iron, cobalt, nickel, selenium, tellurium, we have sulphuric acid electrolyte, they will go into the solution. But there are in this impure anode precious metals. As copper leaves this anode, while these impurities go into the solution, the precious metals simply drop below the anode to form a sludge. Below the anode there will be some insolubles which we call a sludge, and that is contains all the precious metals. So, all the precious metals that were in the original concentrate, they will come all through because they will always be in copper sulphide, and it will end up in the copper finally, and only here it will get separated because other impurities can dissolve. Copper will go through electrolytic refining to the other electrode, and the sludge that comes, the approximate composition is this. This is grams per ton. Silver, gold, lead, arsenic, tellurium, nickel, etc., etc. So, depending on the amount of sludge, considerable amount of these precious metals are collected, and their price actually can account for the cost of electro-refining and many other things. Now, you got a sludge. From the sludge again we have to recover all the precious metals one by one, and for that there is again an elaborate flow sheet. Let me look at that flow sheet. We use the word sludge and also sometimes the word slimes. This is the anode sludge or slimes that collects below the anode. With dilute sulphuric acid leaching, any residual copper that may be in the sludge can be taken into solution. Then there will be the residue. The residue will be treated with slightly stronger H2SO4 and we will do what is called sulfation leaching. In the solution, there will be copper, and copper cementation can give you tellurium, means by adding copper you can get tellurium. The residue by roasting will give selenium oxide, it will go for selenium recovery. There will be a residue which will go for lead smelting to get lead. You will get a metal, it will go through some other process to get another metal, some other step, and finally, we can recover silver grains, etc., etc., and the slime will have gold, platinum, palladium. These are processing steps of chemistry that have been developed over many, many years. So, the sludge that has all these valuable impurities, it can be treated by chemical steps to recover them, and I need not go into the details of this. So, this is the basis of copper metallurgy. But now, there have been developments that, remember once we had talked about flash roasting, flash smelting, etc. When roasting is done in a hearth roaster, where there are rotating platforms and the calcine is going from one bed to another bed to another bed, so that things are exposed to the oxidizing atmosphere, people found that maximum oxidation takes place during flight, not when they are sitting on a rotating platform. It is only when they are discharged from one to the other maximum takes place. So, people argued, why have these platforms, why not let the particles drop from the top straight down to the bottom, and during flight they get oxidized the way you want to do that in a furnace. This is the basis of newer process of flash smelting, means smelting in a flash, and that combines roasting and smelting in one unit. There are different kinds of flash roasters. Here is a cutaway view of Inco flash roaster. You see from here chalcopyrite concentrate is coming here, oxygen is creating an oxidizing environment. So, during the process of this flight, all the reaction that you want to take place takes place. You produce a matte here, you produce a slag here. Now, of course, this means you need to control the oxidizing potential very, very accurately. So, from this side oxygen comes in, because from the end you are putting oxygen, the oxidation potential will be higher here, because you know as you go towards from matte generation of matte, you need higher and higher oxidation potential. So, initially what is happening is the sulphides are getting roasted, then by the time it is coming higher oxidation potential, it forms a matte, and matte comes here, slag comes here. Similar process here is cutaway view of Outokumpu flash smelting furnace. I think it is there in Ghatshila. Here concentrate is coming from here. There is a concentrate burner. This is the reaction shaft, and from here it is the off gases are coming. In the process of flight and the fuel air is all here, you produce slag and matte. So, you have expedited the process of roasting and smelting. They have combined in one step in a flash roaster. We will find that there is a newer process where we will have one more step, the conversion of matte to blister copper is also combined in one step. Those are the ultimate. But the more you combine the steps, more difficult it becomes to control things. You need higher technology. I will come to that in the next lecture. Thank you very much.